Okay, we're going to hustle so that we can actually complete all this in just 3 parts. So this is an incomplete review of Unity Momentum Part 3. Okay, let's do a little ballistic pendulum stuff. Here's a bullet. It has a mass m. It's going to embed itself into a 9m block, sticking in, and then they'll slide across and come to a stop with a stopping distance of x. The coefficient of kinetic friction is mu k. What is how fast was the bullet going before it struck the block? Go ahead and pause and try and find that. Okay, we're back. We're first going to use the work energy theorem to get the energy that it had, the kinetic energy it had right after the collision. So the work energy theorem says this. So let's see, the force on this is going to be mu times, it's going to be the force of friction, so mg, but that's going to be 10 mg. So that's my force of friction times the stopping distance. So now I have the work done, though that's going to be a negative because the force is one way and the displacement's the other. That should equal 1/2 mv final squared minus 1/2 mv initial squared. But v final squared, it stops, and so there you have it. Oh, this should be a 10m, but it's okay if that's a 10m. And this is a 10m. Those are going to cancel anyways. Let's get rid of them. They're on both sides. Let's get rid of the negative. And so V1, V initial, it's looking like it is going to be, I'm going to bring the 2 on the other side. So it's going to be 2 times mu times g times x. Square root it. Okay, then I'm gonna, so that's the velocity. This is the velocity just after the collision. Now I'll use a momentum. Before equals momentum after. So the momentum before is just m times v coming in. The momentum after is 10m times, this is the v. Cancel out an m. And so the v just before the collision, the v of the bullet, is going to be 10 times the square root of 2 mu gx. Okay, that's a tough problem. Okay, next one. Where is the center of mass of this system? Where's the center of mass of this system? I'll see in a little bit. Okay, you know, before we even get started, we know that it's not going to be at the dead center, because if it were that would be at the dead center if there were posts here and here. So it can't be there. It's going to be pulled this way. It's going to be somewhere here. So that's just intuitively, I know it's going to be along this diagonal line and it's going to be somewhere there. But I can find it. Let me find the x center of mass first. That would be the m of this guy times, it's at 0, using just finding this one. So it's m times 0 for the x direction, plus m times L over 2. That's where this guy is. So that's L over 2. And then we're going to divide that by the total mass, which is 2m. So if I cancel out the m's, then I get that that's L over 4. So the x1 is going to be L over 4. And the y1, if I did the same thing again, the y1 is going to be, I'll do this, start with this one again. So it's going to be m times L over 2 plus that m times 0. It's not in the y direction at all. It doesn't have any y value. And that's divided by 2m. So that's L over 4 also. Okay, next one. Cruising here, cruising right along. We're going to finish this no problem. Okay, we have a ball that's going 4 kilograms meters per second to the right, and another ball that's heading it's got its own momentum of 2 kilograms meters per second to the left. Now that's just the magnitude. I should probably put a negative here to show you that it's got it's actually going the other way. This is before the collision. Afterwards, these things, because they're not in line with each other, this one is going to get pushed kind of downward, and this one will be pushed upward. And so afterwards, they're going to have some y components. You want to, if the, let's call this 1 and 2. And this is, here's 2, and here's 1. So afterwards, 1 gets pushed up, and it's got a momentum vector in the y of 1 kilogram meter per second, and it's got a momentum in the x direction of 3 kilograms meters per second. You want to see if you can guess what these two are going to be for the 2 kilogram one? Go ahead and see if you can guess what the momentum will be of the second ball after the collision. Go ahead and see if you can guess that. Okay, we're back. Okay, well, we know that since this had no momentum in the y direction at first, it shouldn't have any momentum in the y direction afterwards. So this has to match that. It's going to be negative 1 kilogram meter per second. This one, the total momentum before the collision was positive 2 kilograms meters per second. So in order for momentum to be conserved in the x direction, this would have to be negative 1 kilogram meter per second. See how that plus that still gives you 2 kilograms meters per second in the x direction? And this give you actually 0 in the y. Okay, lastly, we have here's a ball that's heading the ball is 2m for mass, and it's got a speed v. The other ball is just sitting there, and it's got a mass m. So what is the velocity of the center of mass of this before the collision? So before the collision, go ahead and pause and see if you can guess it. Okay, the velocity of the center of mass before the collision is going to be, it's just going to be, it's going to be m1 times v1 plus m2 times v2, etc. Bump, 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 divided by m total. So that's for center of mass. So the velocity of the center of mass is going to be 2m times b plus m times 0 meters per second all over 3m. So that's going to be, the m's cancel, and that's going to be 2/3 v. So the velocity of the center of mass is not v, it's just 2/3 v. Okay, what do you think the velocity of the center of mass will be after the collision? Go ahead and pause and take a guess. What will be the velocity of the center of mass after the collision? Okay, we're back. Hey, if there's no net force, then the velocity of the center of mass should not change. So the center of mass just keeps going. So after the collision, the velocity of the center of mass should still be 2/3 v. not factorial, just happy to have it.